Good afternoon, everyone. So I'm going to talk about both wire-fed DED and powder-fed DED, with the emphasis on powder-fed DED. So here's the presentation plan. I'll discuss briefly what is directed energy deposition. This will be brief, as most of you know already what it is. Then I'll present the objectives of the project regarding powder-fed DED, and we'll then see the results of DED TI64 repairs, and as well the optimization of heat treatment for such repairs. And then we'll discuss CMT repairs, followed by a small conclusion. So, directed energy deposition. It's a family of processes in which you feed material into an energy source. It can be a wide range of variability of process. Because of that, the energy source can be a laser, electron beam, and arc plasma, and the feedstock can be either powder or wire feedstock. And because of that, you have a very wide range of rate of deposition and final properties, as well as precision into when manufacturing the parts. One of the main interests of DED technologies compared to other additive manufacturing processes such as selective laser melting is that it can be used to add on existing part to repair parts. So this can allow to reduce a lot of scrap when producing parts, and also increase the life of existing parts to put them back in service for the MRO market. So the first objective of this project was to demonstrate the capability of DED and CMT to repair TI64 parts as an alternative to traditional welding, which, because it induces a lot more heat, tends to induce distortion into fairly small parts. So when you want to work on repairs on small section of parts, DED is much preferable because of the decreased distortion as a result, and usually increase in mechanical properties. The second objective is to optimize the heat treatment process for TI64 by DED produced parts. All the heat treatment that we use within this project was based on existing heat treatment within standard. The purpose of that is that clients using the result can directly use those heat treatment to produce part afterward. Why do we need to optimize heat treatment if they already exist? Is that, as you will be able to see, the standard heat treatment proposed in some standard result in mechanical properties that are below the actual requirement from the same standard. So for the powder-fed DED section, we used a lens from Optomec 450 XL, which is their small model. It's all under inert argon atmosphere. And what we use a laser input of 600 watt, which is an actual laser output of 542 watt, and at a travel speed of 40 inches per minute. And the layer thickness are quite small, with 18,000 of an inch per layer, which result in higher precision when building the part, but lower rate of deposition, as what we'll see with CMT later on. So we use both plasma atomized grade 5 and grade 23 powders. The purpose is that a lot of clients have concern regarding oxygen pickup in additive manufacturing processes, and even though standards such as the AMS 4999A requires you to use grade 5 feedstock, a lot of people want to use the grade 23 with the objective of alleviate the concern of oxygen pickup in order to stay within the grade 5 requirements. And the particle distribution that we use is fairly standard for DED. It's with between 45 and 150 microns. So here we can see the part It showed porosity on the top section. It was all machined and rebuilt using the lens system, all under argon atmosphere. And following that, because it's a horizontal repair, we produce multiple samples to evaluate the properties of such repair. For the heat treatment, since it's the standard for DED is for repair with DED for titanium is the AMS 4999A. The original heat treatment that we used was based on DED, using the HIP plus an annealing, but the annealing is at a fairly high temperature at 915. Meanwhile, as you'll see, the requirements cannot be reached with those conditions in certain composition like the grade 23. So we applied various heat treatments that are allowed between the 4999A and the 2801B, which is a standard for heat treatment, and different heat treatment based on variation on that. So as you can see, we've also used only hipping and compare them with without the effect of hipping, so same condition of heat treatment, but by removing the pressure. And similarly, we've worked with the annealing at 704 within the 2801, but we also tested hipping at that temperature to evaluate the effect of hipping under such condition. And as well, we tested various heat treatments, standard heat treatments such as solution treatment and aging, and solution treatment and overaging. So here is the actual microstructure of the repair. It's quite bright here, but you can see a very sound repair with columnar grains in this case. But it's very good microstructure with harness that are well within the requirements for casting, that the maximum is 39 HRC, and in all these cases, be it the actual repair, the interface and the as, and the bulk material, we're below, far below this value. So here you can see the results for the various heat treatment, the evolution of mechanical properties, and you can see that the requirements of with the AMS 499A is, this number are quite small, is 800 MPa. And if you do an annealing at 915 during 2 hours at this temperature, even with grade 5, you won't reach the yield strength required by the standard. And this is even below the requirements from the ASTM B367, which is of 825. And it gets worse if you look at grade 23. With grade 23, you'll see yield strength that is below the required strength for annealing at this temperature, but as well if you do HIP plus anneal. Meanwhile, if you only perform the HIP, you actually obtain higher strength. And this is most likely because the application of pressure prevent coarsening of a certain aspect in the microstructure. The actual alpha late are the same width between both processes, but the beta interlamellar structure is much wider when you're only annealing than when you're only hipping. And then you can perform some aging after HIP plus annealing, and you'll obtain the boost in mechanical properties to be sufficient to meet the standard. However, it's much more ideal to use different heat treatment. If you look at the 2801 heat treatment, the 2801 standard heat treatment, it's using an annealing at 704, so the temperature is much lower. And since the microstructure with powder-fed DED is fully martensitic when as built, then you'll be able to perform a martensitic conversion and thus obtain a quite high strength. So if you look at annealing at 2 hours at at 704, you have a yield strength that's above 1000 MPa, and you still have 13% elongation. Meanwhile, if you do the HIP at the same temperature, the strength will be even higher a little bit at 1060 MPa with the yield strength, and you still have 9% elongation, which is quite above the 6% required by the both standards. Meanwhile, those requirements in a lot of application, it will still be required to do some hipping for various concerns. So if you need to do hipping, hipping only can produce quite high mechanical properties. And then again, for various requirements, a lot of people do hipping and then another heat treatment afterward. Then it should be an annealing at a relatively low temperature, so the 704, in which you'll have quite high mechanical properties over here. And as you can see with the HIP plus SCOA, it provides high strength, but HIP plus SCOA is a quite complex heat treatment. So you do your HIP, then you do your solution treatment, most of the time in air furnace because you need to quench in water afterward. And then you do an overage, so you have alpha case formation, and it's much more complex. Meanwhile, you have the same mechanical properties with only a HIP plus anneal or even a HIP cycle. And then with grade 23, similar results can be observed. So the ideal heat treatment would be only to anneal at 704, since in this type of process, you'll have close to 100% density. In this case, it's higher than 99.9% density in the produced part. So only annealing at 704 will produce very good mechanical properties. Then it's understandable if you need to do HIP, then it can be done with HIP plus anneal, or HIP alone will produce significantly good mechanical properties. Then, if we look at cold metal transfer. So cold metal transfer is another DED process. It's a welding process in which the arc is halting relative colder. And because of that, it's easier to get a steady state as you build parts. If you look at the right, it's an aluminum part built with this process. And those are two examples that I'll show you of titanium. Here is a repair on a 5 millimeter thick plate with very low distortion and a 2 millimeter deposit on top of it. And the second aspect is if you need to use a drilling shield. So the actual melting pool is protected by argon, by local shielding, but on the left you see using a drilling shield provide very low oxidation. On the right, you see the surface is oxidized. But if you look at the microstructure, the actual alpha case is only 250 microns thick. And since your machining requirements will be greater than that, you can work without a drilling shield in some cases, some application, and you don't need to be fully in atmosphere when you're using DED with wire. And the core, there was no significant oxygen pickup in this case without drilling shield. And we can see, well, we cannot see it very well in this case, but there was no alpha colonies growth over there, and there was no oxygen pickup in this case. So you can, in some application, work without drilling shield at all. No need to repair with TI64 under a full bubble protected by argon, which is not the case with powder fed. Since powder, there's a normal surface, it's much more reactive, and you need to be under atmosphere. So in conclusion, the as-built process for powder DED produce fully dense part. Every treatment that ends with an annealing at 900 Celsius results in low strength for grade 23. Meanwhile, every treatment that uses a low temperature Merton-Set conversion results in low ductility for grade 5. The highest yield strength and UTS combination is usually at the heat treatment with 704 as the final heat treatment, actually the only one, so either HIP at 704 or anneal at 704. And you can do IP plus SCOA with very good mechanical properties, but it's a complex heat treatment that you don't need to use if you have alternative, such as, finally, the only HIP at 900 Celsius or A plus anneal at 704. Those are the combinations that provide the best combination of strength and high elongation. And then CMT can be used to repair and rebuild TI-64 with or without a trailing shield with minimal oxygen pickup. So those were the results for project on TI-64. For upcoming project, we'll be working a lot on producing alloys that are hard to obtain on the market in powder form, and as well developing new alloys in order to be able to develop this type of process, the DED and the optimization of heat treatment with various powders. This will be allowed with the two new equipments that we'll get, which are an RCAS gas atomizer and a Tecna plasma atomizer, in order to be able to accompany companies all throughout the process of developing part with new alloys. Thank you very much.
I would like to thank again all our speakers. It was very interesting presentations, and yeah, we are kind of ahead.